So in the previous lecture we derived the equation for strain energy due to axial loading, and that was U is equal to P square L upon 2AE, that we derived. Now we are going to find out the differential equation, right? So I think that is, suppose we have a rod which is fixed at one end, and another end you are applying the P force. Now suppose out of this we only take a little thickness of say dx, right? So the equation for strain energy stored in this small element, that is du is equal to capital P square into dx divided by 2ax, that is the cross sectional area at section x, into E. And if you want the suppose here the x is equal to 0 and here x is equal to L, so we do the integration, you will get the equation for the strain energy U is equal to integration 0 to L, that is P square into dx upon 2ax into E. So this is the general equation for the strain energy, and we derived here as the strain energy equation. So now we consider that about bending, right? Now our aim is to find out the bending. So we find out the equation for the bending, right? Equation for the bending. Suppose we have a beam. Which is simply supported, and if we applied the moment at the mid span, that is the M. So initially the moment is 0 and we increase the moment up to the M, magnitude of M, and due to that at 0 you have the slope. Suppose it is the slope, that is a theta is equal to 0, that is what is called as the I also. We denote it as a I, that is a slope. So as you increase this moment, as you increase the magnitude of the moment, then there will be a deformation of the beam, and the slope at each end, the slope. So initially when M is equal to 0, your slope is 0 because your beam is horizontal, because no moment is there. As you increase the moment, there is an increase in the slope, and it will reach to this maximum slope, and this maximum slope is suppose delta I, right? So if you applied the moment from 0 to M, then the strain energy stored due to the moment, that is du is equal to 0 plus M divided by 2 into, now here work done is equal to moment into the slope of the rotation. So here it is di, right? Di. So indirectly that du is equal to M by 2 into di, and if we prepare that, I think in the simple bending theory, this di, simple bending theory, di is equal to M upon EI into dx. This is in the simple bending theory in the engineering mechanics. So we replace the value, that is equal to M by 2 into M upon EI into dx, right? So here we put the value over here, that is M upon EI into dx. So it is M square upon 2EI into dx, and that is your general equation for your strain energy, right, due to the bending. I think if you have any confusion regarding this di, so I think in the di upon dx is equal to, here that is your slope to the your dx, that is your length, right? So di, now here I is dy upon dx. So let me show what does it mean. So when you have this slope, so this is the x distance and this one is the y. So your slope, that will be the d, that is y by x, right? Your slope will be y by x. So indirectly that is for di, that is di is equal to dy by dx. So here I will be dy by dx upon dx. So indirectly it is d square y upon dx square, and this is what d square y upon dx square is equal to m upon ei. So indirectly your di upon dx is equal to m upon ei. So di is equal to, so we just di is equal to, so di is equal to m upon ei into dx, and that value we put over here, right? So this is your generalized equation for moment, that is a strain energy stored in the body due to the moment. And if you want the same equation here, then it will be u is equal to integration of 0 to L is equal to m square dx upon 2ei, and this is your equation for strain energy stored due to the bending moment.